thank you, PyData, for hosting us and actually allowing us to be one of the corporate sponsors for the conference. Of course, we do it with a reason. We want to recruit the best, we want to hear the best, we want to see the best. But right now, we will talk about, as you can see in the lower left corner, we have JP Morgan there. So it is a bank, and we'll talk about how to manage Python at large scale without breaking the bank. So I'll talk to you about first a little bit about JP Morgan and Athena. Athena is a platform that runs in one of the parts of JP Morgan, and it is a Python-based platform, so I'll describe to you what Athena is. We'll talk about some of the objectives that we have in our ecosystem. We'll talk about continuous delivery conceptually, and we'll also look at how we do this under the hood. Then we'll talk a little bit about challenges with dealing with a large Python-based ecosystem, both from the point of view of how we manage it and from the point of view of challenges of dealing with open source software, and we use a lot of open source. And in the end, we'll finish with some conclusions and hopefully a good Q&A session. And hopefully this will work. All right. So JP Morgan, I don't think it needs a lot of introduction, so I'll briefly run through the numbers. One of the world's biggest banks, trillions of dollars in assets, almost 100 billions in revenue, processing trillions of payments every day, and millions and millions of transactions every day. We are really large company with 230,000 employees all over the world. At the same time, we're also one of the world's biggest technology companies. And this is a pretty massive scale. We have over 40,000 technologists working for the bank. And I would hope, and I would imagine, a lot of them are developers. Not necessarily Python developers, but developers in different languages. Cabal is probably not the most popular one, even though some people view banks as still being in Cabal stage. We do massive investment in technology, almost $10 billion every year, and these technology investments pay off. That makes us one of the world's biggest banks and one of the more successful ones. Now let me jump from JP Morgan to Athena. Athena has been envisioned just over 10 years ago as a cross line of business within the investment bank, Python-based pricing, trading, risk management, analytics platform with tools for data science and machine learning. Well, to be honest, the data science and machine learning, the conference organizers asked me to add at the end because they said, if you don't add machine learning to your presentation, you're not allowed in this organization. So I had to add it. Seriously though, we are actively working on multiple machine learning projects, and actually if you step outside to our booth, we have a number of quants also attending this conference who are very actively building machine learning packages. We have a data science team which is using a lot of these packages within Athena environment and outside of it as well. And we are also actively looking for more people to contribute. So we have thousands of users across multiple lines of businesses: credit, FX, rates, commodities, equities. There is a very wide user base for the Athena platform. We have 1,500 Python developers who not only use the platform to develop code within the platform, but also to contribute to the platform itself. The whole platform works as an internal open source project, so you can see the entire code base and you can contribute it very, very easily. Over the years, of course, we have built out a very large number of Python modules or files, 150,000 Python modules as of last count, 35 million lines of Python code, all living in a single repository. I'll talk about it a little later. We use massively, as I mentioned, open source, over 500 plus packages from the open source community. And our philosophy is to enable developers to deploy very quickly and develop very efficiently so that they can impact the business very, very rapidly. So a little bit more about Athena and its technical foundation. We build a lot of stuff ourselves, and a lot of things have been built before similar concepts existed in the open source community or were stable and reliable enough to use. So we built our own globally replicated object store called Hydra. We built a complex event processor. You can think of it as a reactive data flow graph, which we use for streaming events and streaming trades and connecting to exchanges and all kinds of other streaming analytics. We have a pixie graph, which is essentially a lazy evaluation dependency graph, which allows us to run efficiently complex analytical calculations where some dependencies change and some dependencies don't. A typical example of that are risk scenarios where some market data changes and some doesn't. So we only recalculate what needs to be recalculated and keep around what doesn't change. We have a number of frameworks. For thick client deployments, Athena application framework. For the web deployments, we use modern tools that are available in the web ecosystem. We built our own job scheduler, which runs on thousands of compute nodes, scheduling around 270,000 jobs daily with over 1 million processes running daily. And we integrate with internal compute grid, which is sort of a predecessor of a cloud technologies, which has hundreds of thousands of compute cores and GPUs. So that allows us to run massive scale calculations. So all of this runs on a single Python-based platform with some underlying C++ components for the foundation. So what are our objectives? Well, of course, the primary objective is keep end users and clients happy. That's a goal. At the same time, we need to ensure robustness and stability of our production systems and keep developers productive and efficient, because that also makes developers happy. And that's important, otherwise they leave. We need to provide quants and data scientists with quality tools for doing research, and these days, machine learning and data science. So that's another important aspect of it. And at the same time, we want to encourage sharing and global consistency across business lines. We don't want different lines of businesses have a different idea of what an option pricing is or how a market data is represented, because that way they will end up reinventing the wheel over and over again. So we want to be able to actually share and reuse those components. So now let's take a look at how we approach those objectives. One of the primary concepts in Athena is a concept of continuous delivery. We are actually able to change production code thousands times a day. I just ran some stats last night and added this to the slide. We actually do 10,000 to 15,000 production changes every week in our Python code base. This is massive. So how do we keep at the same time production safe and stable is a challenging task. We also want a full visibility of the entire code base. One reason for that is everyone can contribute. People can move from one line of business to the other and still be very familiar with the entire code base and how everything works. People can share knowledge and share code base and share Python modules. We also need something that allows us to deploy our code into production globally and instantly. we want the same risk model to run in Tokyo as we're running in New York or in London. So it is also one of the important underpinning cornerstones of Athena. What do we use under the hood? And this is very brief, of course. Under the hood, we actually use Hydra, which is, as I mentioned earlier, our globally distributed object store. And we not only use Hydra for data, but we also use it for code, because code is nothing more than just a file, which is data. So having this replicated, globally replicated object store allows us to have code instantly available around the globe. To address sharing of the code, we have the entire code base in one large mono repository. And even though lately the ways of storing code using Git and other version control systems became more and more popular, you can, and I will actually in the end will reference a paper by Google, how they also use a single repository for storing billions of lines of their code. And of course, all of this relies on the extensive automated testing. So the pipeline for continuous delivery is actually ridiculously simple. You write some code, you write some files, you write some tests for your code, then you test, you commit, and the point when you commit, we also run another set of tests just to make sure that what you're committing is actually consistent. You're not just allowing you to test somewhere on the side and then go on and commit a file. And while you commit, we do other checks as well. We do code quality check using various lint options. Once you committed a file and you feel that it's ready for production deployment, actually you as a developer feel that it's ready to be pushed to production. You change something for a trader, or you augmented something in the risk management system, or you change some other component. You ask for a bless. And it's somewhat similar to a pull request, essentially. Each file has a set of people who can actually say, hey, this is good. So you send a message using basically a button push on in your IDE to say, hey, can you please review and bless it? And once somebody says, hey, your changes are okay, and I bless your changes, he actually takes 50% of responsibility for this being correct. So you actually need to be careful what you bless and not bless blindly. Why? Because the moment you bless, this file anybody can automatically push to production by a button push. And when I mean it can be pushed to production, it will actually end up in the production source code tree, and any process that is importing that file can actually import that process immediately anywhere around the globe in any of the processes. So again, we have 10,000 to 15,000 modules pushed to production every week. It's 2,000 to 3,000 a day, pretty large amount. And I'll skip pros and cons. They're somewhat obvious. Time to market, of course, and fear of change and stability. Yes, of course, and we'll talk about that. So imagine you were a developer and you came into Athena and you decided, hey, I want to write some code. You open your IDE and you have immediate access to the entire monorepo, to the entire code base. It looks to you like a file system, even though I will mention later that we actually store your files in a database. So you can look at the production files down at the bottom and say you want to work on the modules A, B, C, and D, and you want to create a new module called E. You can create as many layers as you want, and those layers are essentially act as staging areas. So you open your environment, you read a file, say B, and you want to create a new version of it. You create a new version of it, it immediately becomes a member of your layer. There is no process of checking out a whole repository. There is no process of pulling something in. You actively changing the file, and the moment you hit Control Save, it will be saved in your local staging area. And you can layer those staging areas with essentially kind of a sieve-like visibility rule, so the higher layers overshadow the lower layers. So for example, this particular developer has module B3 and C2 and E1, module B, C, and E in his own environment with versions 3, 2, and E and 1. And he also is using some shared staging area, which multiple developers may be sharing between themselves. And all of this is underpinned by a single production source. So for this particular developer, his view of the world is as described in the lower line. His effective runtime will be picked of these particular versions of files. And it's not only for this developer. He can share this area with anybody else in the bank. So anybody else in any region in the bank who uses Athena can open against this set of staging areas and see exactly the changes that have been done. At the same time, you can run any process on any of the servers in the bank, again, if they're part of the Athena ecosystem, against this set of staging areas, and they will execute exactly this collection of code. And of course, we will not allow this code to alter any production data, so we have a fail-safe so that only modules that are already in the production ecosystem will be allowed to touch and modify production data. So indeed, what do? We, instead of file system to store modules and then do a check-ins and check-outs, we use a globally replicated database to store files. And this globally replicated database essentially syncs transactions continuously between each other. They form a ring. So the file or any object written in London will be almost immediately up to the replication gap available in New York, in Tokyo, in any of the other databases that belong to that ring ecosystem. So we have a module called libfoo, which does something, libbar, and so on and so forth. We had to customize a Python importer to enable this capability to import from the database. But because our database actually looks to the user almost as a file system, that wasn't a very difficult task. Of course, one may ask, if you are pushing to production so many changes continuously, how do you keep your production process stable? Especially since you have one single repository, and in Python, as we know, anything can import anything and drag in some dependencies and keep dragging dependencies in. So how do we ensure that our mission-critical production processes continue to run while we keep pushing changes into the system? Well, we'll take advantage, actually, of the fact that we're storing our files not in a file system, but in a database where things are transactional, and they have timestamps, and they have a lot of other nice properties. So we will ask every owner of a production-based system to create something called source marker. And essentially what it is, it's a reference to a timestamp. The timestamp, when you run all your regression and unit tests and ensured that the entire code base that you depend on is actually good. And for a certain duration of time, the entire production system for this particular application will use the specific time slice of the source database to actually protect him from accidental rogue pushes to production by somebody else unrelated. Overnight, typically, that source marker will move because the tests will run again, and we run the tests continuously. So if the tests run successfully, the source marker advances, and your next day job runs again against the new code base, which has been verified. If it didn't, you will get alerted, and you will have time to actually change your code or work with the developer who did the breakage, because you will remain on the older source marker. So that ensures the production stability while pushing a lot of changes simultaneously into the system. What's running underneath? So I mentioned a lot of C++ based components and open source components which we rely on. So at the top you see our massive Python source, which is our massive monorepository of everything running in Python. Underneath, we have a more traditional development where C++ and open source binaries are involved. This is your typical 2-week cycle of build, compile, deploy, underpinning infrastructure that, including the database itself, including the software development lifecycle components, and all the other components as well. The prod in the center is our current production approved system, and it's deployed globally to all the servers. The prod new is your typical release candidate that keeps changing continuously until the lockdown time before it will become the next prod. And the prod old is kept for safety in case we did introduce some incompatibility into the system. We can always fall back some of the jobs, some of the critical jobs on prod old. And the falling back and forth between those components is very trivial. It's essentially flipping a symbolic link. We strongly encourage all the testing and all the development activity to go against prod new. This allows us to actually validate the release candidate before it becomes production. And on top of this encouragement, we also run an enormous amount of unit tests and regression tests, which automatically run overnight and during the day on a massive compute grid to ensure that the system is holistically stable. So now let's talk about some of the challenges of this environment. I mentioned that we have a high dependence on open source packages. So as you probably know, upgrading open source packages leads to many challenges. Open source community is not always great at maintaining API compatibility. So if you have a massive investment in your numerical stability and computations and risk numbers and reports to regulators, it's really, really difficult to keep adjusting to the API changes, especially for some newer packages. Changes to pickled and stored representations. Well, the great example of this is pandas. You move from one version to the other. If you happen to store millions of data frames in some database, well, that's a wrong idea, but quants love to do that in file systems and in databases everywhere. So now that is really difficult to test because you don't know when this particular object is going to be read. But if you want to move your entire ecosystem to actually more modern version, you need to ensure that it is somewhat compatible with the old stored representation. Numerical changes, that happens again all the time. Just recently, we've been working with a NumPy upgrade, and we discovered through again rigorous testing that in one of the interesting edge cases, a covariance matrix produced by some linear algebra calculation using NumPy was not perfectly symmetric. Well, it was symmetric up to a float point tolerance. The previous version of NumPy had actually perfectly symmetric matrix. So one of the tests was actually testing numerical equivalence exactly instead of using a float point tolerance. So we actually ran into this case where we saw that the result is actually not perfect. And then you need to work, of course, with the quants and with end users to validate, are we still producing a correct number? And this is just one of the examples. Runtime binary dependencies. Another example of open source challenge. That actually happened. That anecdote is happened just the other day. We had a quant who had some program using NumPy and was calculating against some linear algebra, of course, matrices. And then he decided, hey, I want to play with TensorFlow, so he imported TensorFlow into that same process, and suddenly NumPy started producing wrong results. Not crashing, just producing wrong results. So you go through extensive search on the internet, look what's happening, and apparently if you compile both NumPy and TensorFlow with MKL support, which is mass kernel libraries from Intel, you would run into a specific problem where each of the runtimes tries to grab as many threads as possible, and some random thing starts to happen. It is true. So besides open source package upgrades, what other challenges do we face? We do have limited branching support in our massive monorepository. It actually works pretty well for production use cases. You want to keep your changes small and fast and move forward as soon as possible, rather than creating a massive branches of different projects and then have painful merges. It's also quite difficult to have one large testing infrastructure if you have multiple branches of your projects. But this doesn't fit some of the research and experimental workflows where, for example, some researcher may want to say, okay, I want to run several very similar code bases in parallel, and so I may want to create several branches of that. So this is something what we're actually actively looking at and trying to see how we can fit every workflow that is needed for being productive into the ecosystem. And of course, it's very difficult to just freeze the entire ecosystem for full reproducibility if you want to say, I want the entire platform to be frozen, and the next year I want to be able to rerun exactly the same code. We just keep on moving forward. So let me go to some conclusions. Well, Python's flexibility makes things easier. We can create custom importers. We can do some static code analysis to do better testing, and so on and so forth. Good integration tests help us to ensure compatibility and consistency between multiple packages. Modules don't have to be loaded from a file system. Yes, we can load them from a database and take advantage of some of the properties of a database. Production stability doesn't imply slow delivery and slow deployment. We deploy thousands of packages while keeping production stable. So this is not a problem. And open source, of course, doesn't imply free. You still need to invest a massive amount of testing and integration into supporting open source packages. And last but not the least, shared platform, unfortunately, doesn't imply shared knowledge. You have a shared platform with the entire code base visible, but people will still reinvent the wheel, will write their own. Well, because they're developers, they like to develop, and that's how it happens. Or maybe they don't trust somebody else developing the code. Just a couple of references at the end. Please visit us on the website or visit us at our booth right outside if you're interested either in the technology aspect of what we're doing or in the data science and machine learning, I will say these words again, aspect of what we're doing, because our quants are really, really hungry to have more people working with them on these problems. And a motivation for a monolithic code base, please feel free to check out this. I don't know how you can click on it right now, but it's pretty easy to find why Google stores billions of lines of code in a single repository. You can find this offline for motivation. And do I have time for Q&A? Perfect. Yes?
You
need the microphone?
Yeah. Thank you. You had quoted a number, I think 10 billion annual spend on your technology budget. What percentage of that would you say goes towards hardware and software? And on the software side, what portion of that goes towards internal developer salary versus third-party licensing?
Ooh. I'll be very honest with you that I don't have that breakdown. But if you stop by our booth, we can definitely talk about that and discuss that. And I can come with some guesstimates, but since I'm recorded, I will probably not. It's a nice Google-style interview question, right? So I will not embarrass myself trying to guesstimate it. My guess is a very large component goes to salaries. People are still a very expensive commodity, so we actually want to find good people who are usually a little bit more expensive but deliver more.
When you do have to make something reproducible, for example, for a regulatory relevant run, how do you achieve that 100% reproducibility?
Right. That's a very, very good question. And 100% is usually a target, really a wishful target to hit. I would like to separate, in terms of reproducibility, the code, the model, and the data. So having the data represented in such a way that you can actually reproduce what happened is extremely critical. One of the answers to the regulators is you don't have to rerun something. As long as you have it already available as a result of your calculations, you may be able to just return that. So if you have a correctly structured bitemporal store, you should be able to have a capability to actually reproduce it from already saved data. You don't have to execute exactly the same binary code to get that. So that would be one of the ways to get the right numbers and the right calculations and not run exactly the same binary. And of course, models are very thoroughly governed. So we have, for the quantitative models, for the critical models, we have governance groups who actually look at the fact that your model continues to perform correctly. They have ongoing performance assessments and so on and so forth. So we have ways to actually ensuring that the results that we produce are still consistent while we may be running a different version of a code.
So obviously, a data scientist is not quite a software engineer, and a software engineer is not quite a data scientist. So say you have like a data science use case, right? You're trying to predict something. Your data scientist is working out what the best model is and is developing a script to execute against whatever it is you're doing. I guess my question for you is, and I lead a data science program at a smaller company, like then what? You've got your solution developed, you're ready to, you have something that looks like production. I guess, how does JP Morgan handle the situation? Who maintains the code? Who writes the tests?
I got it. Very good question. So actually, we try to have, and I don't know if that's the right way or the wrong way, but this is the way we do it, is our quants, and currently they are the main data scientists, actually write the code and write the tests, and they integrate with components. And we try, that's why we actually built out this large ecosystem to relieve them of the need to write data cleaning routines or adapters to various databases. So all the foundational framework is already there. You should write your model. Hopefully, as a quant, you're a smart person. You can write reasonable code as well and have tests around it. All the quants are developers as well at the same time. And then you essentially can have this model both developed in the environment, tested in their environment, and deployed in the environment. So you're not essentially changing, you're not taking some abstract model developed in one language and then giving it to a developer, hey, please can you interpret that into a different language, which leads to all kinds of challenges.
So obviously, building a system like this comes with some design considerations that are taken into account that kind of puts you on a road that everything has to be comply on. So is the paradigm that you subscribe to that everything has to be backwards compatible? So like once you put something into the system, it will work forever, or is there a versioning where
actually, it's almost the other way around. We try to move the whole ecosystem forward. So it's a fix forward rather than fall backward methodology.
So then, so how does that work in practice? Do things just like fall off as they stop working, or?
No, they don't stop working. Well, if they become irrelevant, they stop working, and you delete the code. Hey, hooray! We deleted some code. This is awesome. But if they're actually needed for production, well, we have teams that support that code base. If you want to move the whole train forward, these teams help to move the rest of the platform forward and adjust. So if we do release, and we do have, so it's a trade-off, as you correctly pointed out. And the trade-off is, for example, do I want to have 20 teams running, let's say, for example, each of them running a different pandas and different numpy, and then managing that deployment? Or do I want all the teams be on a single or, say, two versions? I probably actually, for efficiency, again, going back without breaking the bank, for the efficiency, for the consistency, I would love all of them to be living on the same version and marching forward. So we do have to move things forward rather than keep them deeply backward compatible. I don't know if that answers the question or not. Yeah, we can chat after. Happy to chat after that.
Any more questions?
Hi. What are the methods used to prevent reinventing the wheel? How do quants find other code? Is there... Okay.
Of course, yeah. Good question. Sometimes you cannot prevent it, and I will actually even tell you a little anecdote. I needed to write a function that chunks a list or an iterable into fixed size components. And first I thought, well, this is a very cool and easy function to write, and I will just because I like writing code, I'll just write those few lines and write them correctly. And then I decided, well, how about I first use our internal search tool called Glimpse to see if somebody already wrote something which looks like chunk or chunkify or something like that. So I decided I did Glimpse def chunk. I found 145 instances. Some of them were incorrect. Some of them were exact copies of the others. Some of them were correct, but would take an extra argument which limit their capability or will alter their behavior. So yes, it's a very valid question. At the same time, we have full visibility of the code. So if you probably will search for volatility, you will find all the code which is related to constructing volatility surfaces, and then you can drill down and see who developed that, what the history of the changes are. You can reach out to that person and say, hey, I see you built this. How can I use this? The next step would be actually building, and that's what within my team, and actually a couple of people from my team are sitting right there, we're trying to build out essentially a knowledge base or knowledge repository which will help quants and data scientists at a higher level define what they're doing, and make this metadata more easily searchable so that you can actually share knowledge at a higher level via Jupyter Notebooks, via some website, via some other interactions.
Thank you very much, everyone. Thank you, Misha.
Thank you.
Welcome.